Hi everyone, this is the second part of the video on chord length and arc measure, so I suppose I should really be calling this part 2, and this gets into a little bit more of the mechanics of working with these circles. Alright, so we've already talked about the vocabulary, we've talked about the wording, and it is important that you know all the terminology because there's going to be a lot of words thrown at you, and it's important that you know what parts of the circle they're talking about. Okay, we're going to start out with something called the chord center theorem. The chord center theorem looks very intimidating. All right, there's a lot of pieces to the chord center theorem that really are all just almost the converse of one another. Okay, it's not quite that direct, but there's a lot of information packed in here that hopefully you'll see is not as difficult as it sounds. So the line that contains the center of the circle, so we're talking about this line right here, contains the center of the circle and is perpendicular to the chord. So that's what you're seeing here, is that there's a right angle. Bisects the chord. So if you have this situation, you have a line going through the center of the circle and it's perpendicular to the chord, then it must bisect the chord. And remember, bisect means it cuts it exactly in half. Okay? So you now know that those two pieces are equal to each other as long as you have this right angle right here and as long as it goes through the center. Okay. The line that contains the center of the circle, so again, talking about this, and the midpoint of the chord, okay, so if we know that it cuts the chord in half, bisects the central angle of the chord. So if we've got this situation up here where we know that it bisects that chord, okay, we know that this is the midpoint, then we know that this line also cuts this angle in half. So if you draw that line out to the tips of the chord, that angle is also going to be cut in half. We know that these angles are equal. Okay, let's look at a couple other pieces. The bisector of the central angle, so this is kind of backwards from what we just talked about. So if I have this line, whoops, did not mean to do that. If I have this line, and I know that it cuts this angle in half, so I already know this, then it's the perpendicular bisector of the chord. So now, if I know that it cuts the angle in half, I also know that it cuts the chord in half, and it's perpendicular to the chord. And the perpendicular bisector of the chord of a circle contains the center of the circle. So now if I give you a segment and say, hey, we don't know anything about this line, but we know that it cuts this in half and it makes a right angle, it has to go through the center of the circle. Okay, so we would know that center of the circle is point P. I know that's a lot to wrap your head around, so let's kind of summarize that. In this situation here, if you've got this line that goes through the center of the circle, you know several things. You know that these angles are congruent. You know that that angle is cut in half. You know that you have a right angle right here. And you know that these two pieces are congruent. Okay? For the record, you also know, this is sort of doesn't have anything to do with the chord center theorem, but this is important. You also know that these sides are congruent. How do you know those sides are congruent? Think about it for a minute. Those segments from P to L and P to N are both a radius of the circle. And any radius I draw is going to be congruent to each other. So this segment would also be congruent to those two because it's also a radius. Okay? I could draw another line over here, and this would be congruent to those as well. This is going to be important because you're going to start to do some stuff with those triangles you see in there. Okay? SAS, SSS, any of that sounding familiar? That's all going to come back into play here. So let's look at some examples. Find the length of the chord of a 103-degree arc in a circle of radius 20. Okay, so let's talk about what the wording is saying. Find the length of the chord. So remember, the chord would be this, from L to N. So I'm trying to find this, of a 103-degree arc. So I know this measurement is 103 degrees. And then the circle has a radius of 20. That's these pieces right here, from P to L and P to B. Okay, so from P to L and P to B, I know that distance is 20. Because they're both a radius of the circle. The other important thing to notice is remember that the central angle is always congruent to the arc. So you know if this measurement is 103, then this measurement is also 103 degrees, that angle. Now let's look at what we have here. I'll actually move this off to the side here, because I want you to see that what I now have is this. This is 20. This is 20. This is 103. And this is what I'm trying to find. Does this look familiar at all? Hopefully this should look like the test you just finished. Okay? I don't have angles and sides that match up, but I could set this up with your very favorite law of cosines. Let's call this side A. Let's call this angle A, my B and my C. And I would write it out as A squared equals 20 squared plus 20 squared minus 2 times 20 times 20. Oh no. Here we go. Times cosine of angle A. So cosine of 103. Now luckily, this is one of the easier ones where I can just type this whole mess straight into my calculator. Let's give that a shot. I ended up with A squared equals 979.96. And then from there, let's take a square root. I end up with 31.3, and that's your length of the chord. Okay, so once you get those numbers on the picture, this goes back to very familiar territory, so hopefully you're still comfortable with this stuff. Okay, so now we've got 3 of these exact same problems to do. It says a circle has a radius 10 inches, and then it wants you to find the length of all of these chords, depending on the arc length. So the only thing that's changing every time is the length of the arc. I shouldn't say length of arc, the measure of the arc. Okay, because we're not really measuring the length, we're measuring the degrees. So if I look at this first one, it told me in that problem that my radius was 10. So I know each one of these sides is 10. And if this arc is 60 degrees, that means this angle is 60 degrees. And I'm trying to find the length of the chord, which is this. And I'm just going to go ahead and label that side A. I'm going to ignore these other letters. And I'm going to set this up with the law of cosines. So this would say A squared equals 10 squared plus 10 squared minus 2 times 10 times 10 times cosine of 60. That's all law of cosines. Okay? Stuff that you just finished doing. Let me type that in. For this one, this is kind of strange, but you end up with 100 exactly. That's because of the value of cosine of 60. But so A squared equals 100. Take a square root, and A equals 10. Which should make sense because if these two sides are equal to each other, okay, and this angle is 60, we know these two angles have to be equal. So if I subtracted from 180 and divided by 2, I would get that these two angles were also 60. This is an equilateral triangle when this is 60 degrees. Okay, so 10, 10, 10. Let's look at a 90-degree one. So again, the only thing that's changing here is the angle measure. This angle measure is now 90, but you still have a 10 and a 10 on the sides. Okay, so I'm going to set this up as A squared equals 10 squared plus 10 squared minus 2 times 10 times 10 times cosine 90. Another strange one comes out to A squared equals 200 exactly. Let's take a square root of 200. And when I take a square root, I end up with A equals 14.14, which would be the length of this side from D to F. And let's try one more. Again, the only difference being now I'm changing the measure of that angle. So this is still 10 and 10. My radius is still 10. Now my angle is 120 degrees here. So my setup would look like this. A squared equals 10 squared plus 10 squared. Are you getting bored writing this down yet? I want you to see how easy this is. Times cosine 120. It might be hard to see, but it says cosine 120. Okay, let's type that in. This one comes out to be 300, which when I take the square root of that, I get about 17.3. Okay, so my whole goal here, whoops, that cosine 120 is supposed to be attached down here. My whole goal here is for you to be able to look at all three of these, okay, side by side, this one, this one, this one, and see that they're all done exactly the same way. The only thing I changed was the angle measurement at the end. Okay, so really this should be sort of a no-brainer when I ask you this question. Okay, last example. Here's a way we're going to kind of put this all together. I think, let me pull this in a little bit so you can see. I gave you the definition here of an inscribed polygon, just because you're going to need to know that to be able to answer questions like these. An inscribed polygon is a polygon like this one, this octagon, where all of the vertices are located on the circle itself. So this is almost like this octagon is trapped inside the circle. Now we do know this is regular, meaning all these side lengths are going to be the same. Okay, that's going to help us out quite a bit. But we want to find the perimeter. So ultimately, we want to be able to say what is the length of one of these sides, and then we could take that one side length and just multiply by 8 because they're all the same. So let's think about how we could get one of those sides. I know the distance from the center of the circle to any one of the vertices. Okay, I could draw all of these in. I'm not going to draw them all, but you get the idea. The distance of one of those black segments I just drew is 8 centimeters. Okay. 8 centimeters, which means they're all 8 centimeters. I'm not going to take the time to write them all in, but you could if you wanted to. Now we could do this almost like the problem we just did. The only thing is we need to know this angle. Okay? I want you to think about this. If we did draw these triangles in, I guess I am going to draw them. How many would there be? Starting here, 1, 2, 3, 4, 5, 6, 7, 8, which hopefully makes sense because it's an octagon. And all the way around the circle is 360 degrees. So around the center of the circle, there's 360 degrees to be split up among these 8 triangles. So I'm going to start by doing 360 divided by 8. And I end up with 45 degrees. So that means the top of each one of these triangles is 45 degrees. Let me make that picture bigger. There we go. And what I really want is the length of this side down here. So I'm going to hit law of cosines just like I did before. I'm going to call this side A. I'm going to call this top angle angle A. And I would set it up as A squared equals 8 squared plus 8 squared minus 2 times 8 times 8 times cosine 45. Let's go calculate that. I end up with about 37.5. And then when I take the square root, I get that A is equal to about 6.12. So that's the length of one side. Now if I want the perimeter, I want the length of all the sides. And I have 8 of them because this is an octagon. So to get my final answer, I guess I'll journey up here. Let's just do this. To get my final answer, I'm going to take that 6.12 and multiply by my 8 sides. And it's going to be right around the realm of, I'm going to take a stab at this, 48.96. Let me go double check that for you. Yep, that number is exactly right. So that number is the perimeter of the octagon. That's your final answer right there. Okay, so I did the same thing I did before, but now I just applied it to a perimeter problem by finding all of the lengths and then multiplying by how many I had. Okay, that should be enough to get you going on the first assignment. And on Tuesday, we will pick this up with, what's next? Inscribed angles in a circle. So today we talked about central angles. Coming up next, inscribed angles. Have a great day.